Okay, today we'll start with total internal reflection. Okay, so what do I mean by total internal reflection? So let me take the side heading, total internal reflection. Usually, what do we mean by reflection? Reflection in the sense, so when a light hits a interface, so if it is bouncing back into the same medium, then we can say that is nothing but a reflection. So what do we mean by total internal reflection? And what is the cause for total internal reflection that we are going to discuss now? Have a look. So let me take a shape like this. Yes, exactly. So here I'll take normal, different normal to the surface. Okay, now let us say that a light ray is traveling from denser medium to rarer medium. I'll take the medium here as denser. I'll take the medium here as rarer medium. Okay, whenever light ray is traveling from denser medium to rarer medium, how it should bend? Will it bend towards the normal or will it bend away from the normal? So this is denser medium. From denser medium to rarer medium, it is traveling. How it should bend? Will it bend towards the normal or away from the normal? We have spoke about the refraction already. Refraction is nothing but bending phenomena of light when it is traveling from one medium to another medium. Okay. So it will bend away from the normal, right? Good. So whenever it is bending away from the normal, you can clearly see that it will try to take a bend like this. Okay, let me take the elementary bend like this. So for an incident angle, let me write the incident angle with the normal like this. Here I can get the refracted angle as some R. Okay, let me call it as I1. Here R1 I'll take it. Next case I'll take. So if you increase the incident angle a bit more, here I'm increasing the incident angle a bit more, then how the refracted angle will be? The refracted angle will also be increased, right? Yeah, the refracted angle must be like this. There should be more and more bending. So at one point of time, what will happen? For a given angle, for a given incident angle, so if this is the incident angle, at one point of time, let me call it as some I3. If it is I2, for a given incident angle, the refracted ray becomes parallel to the interface. Okay. Whenever this phenomena happens, then what this angle called? Can anyone tell me? For a given particular incident angle, the refracted ray becomes 90 degrees with the normal, or the refracted ray becomes parallel to the interface. That angle is known as critical angle. Clear? Good. Critical angle. So this I3 is also called as critical angle. Now you can clearly see here 90 degrees with the normal as well as refracted ray. Now if you increase an angle more than the critical angle, assume I'm increasing an angle which is more than critical angle, whatever the given I must be greater than IC. Then what will happen? Instead of entering into the rarer medium, the light ray will try to take a bend away within the same medium. So instead of bending, it will be reflected within the same medium. Okay. And if it is reflecting, the incident angle IC will be equal to R. Even I can say that R will be IC. Same reflection, no? The incident angle as well as reflected angle both must be same. So here we can clearly see two definitions. One, we can take the definition for critical angle. The other, we can take it as total internal reflection. By any chance, if the incident angle is greater than the critical angle, then we can say that instead of getting refraction, we are getting a reflection internally within the same medium. This phenomenon is said to be total internal reflection. And critical angle in the sense, For a given incident angle, if the refracted ray becomes 90 degrees with the normal, then we can say that that incident angle is nothing but the critical angle. Okay, here I'll tell you two definitions. Just a minute. Yeah. So you can note down two definitions: critical angle as well as you can go for total internal reflection. Applications of total internal reflection is very huge. Total internal reflection and critical angle. Okay, what do you mean by critical angle? So for a given angle of incidence in a denser medium, the refracted ray becomes 90 degrees with the normal. So here you can say that this given angle is termed to be, or the given angle of incidence we can call it as critical angle. IC we can make it. Okay. Now total internal reflection in the sense, so by any chance, if the incident angle is greater than the critical angle, then we can say that the ray will be reflected in the same medium. You can say this one as total internal reflection. That's it. Totally the ray is getting reflected. You can say that total internal reflection. That's it. And than this, in board they'll ask you this question. So in order to get total internal reflection, what are the necessary conditions? Directly they'll ask you this. So what are the two conditions? Usually you can mention two conditions. Okay. Can anyone tell me what are the necessary conditions? Conditions for total internal reflection. TIR will say. Okay. Yes. First one, you can clearly say that the ray must travel. The ray must travel from denser to rarer. From denser to rarer alone. From rarer to denser, this phenomenon will never happen. So I can give you one more. What is one more? The angle of incidence must be always greater than the critical angle. Then only this total internal reflection will happen. Other than that, it will never happen. Good, good. Nice. Okay, I'm getting nice answers. I hope this concept is more clear for you. So I'll give you a quick analysis why it will not happen when a ray is traveling from rarer to denser. Assume I have taken a normal ray, a simple ray. Here, this is the angle of incidence. Okay. Now, whenever a light is entering from rarer to denser, how it should bend? It should take a bend towards the normal, right? So I'm taking a bend towards the normal. Each and every time, whatever you do, the light ray is bending towards the normal only. It is not going away from the normal. In order to go from a denser to rarer, I should say that the ray should bend away from the normal. Whatever you do, the ray is bending towards the normal, where we can't observe the total internal reflection. Clear? Okay. That is the reason you can say. Okay. Let me switch. Okay, this is a concept of total internal reflection. Okay. Now, yesterday we have taken, right, Snell's law. Can anyone tell me what do you mean by Snell's law? Just a minute. Just a minute. Yes, sin A by sin R we have taken. Okay, you can clearly write Snell's law we are talking, right? Now, whenever you are dealing with the Snell's law, have a look. Sin I by sin R, everyone is saying. So I will clear the Snell's law part. Sin I is nothing but this, sin R is nothing but this. But sin I by sin I is equal to what? Can anyone tell me? You will have a different thing. By any chance, if eta 1 is a refractive index of rarer medium, if eta 2 is a refractive index of denser medium, now can you tell me that what is sin I by sin R? Is equal to what? Sin I by sin R is equal to, yes, it is constant. But is equal to what constant? Is it gravitational constant? Spring constant? There must be a value for the constant, right? So I can clearly say, I'll give you a clue for Snell's law. So whenever you are taking sin I by sin R, you should always write it as some n1, eta 1 divided by eta 2. Or I can write it as eta 2 sin I must be equal to eta 2 sin R. Oh, just a minute. Eta 2 sin I equal to eta 1 sin R, it must hold true. I'll give a clarity on it. Wherever you are having the incident angle, whatever the angle it is, that corresponding refractive index must be taken. See here, I know for I, n must come. Here for refractive index, so for refractor ray, for R, n1 must come. See, for R, eta 1 came. For I, eta 2 came. So both are on the same sides now. I and eta 2. So I and eta 2 are on the same sides. Eta 1 and R1, they are on the same side, right? So I can say eta 1 and R are the same side. Based on that, you can make this formula more clearly. Is that clear? Most of the students will make a mistake while drawing the diagram and writing the equation. Please make sure. Okay. Sin I by sin R is equal to rarer by denser. Refractive index of rarer medium by refractive index of denser medium. Fine. Is that clear? Okay. Let's proceed further. So now I can say that, so whenever you are taking the Snell's law, I can very well write eta 2 sin I. I have taken eta 2 in the diagram. Eta 2 sin I is nothing but eta 1 sin R. So you can write it as sin I by sin R. Eta 2 by eta 1. Sorry, eta 1 by eta 2. So this one is a rarer medium. This one is a denser medium. Please make sure. Whenever you are substituting the eta part, you must not make any mistake. Okay. We'll give some special cases. Even you might have found this in your NCERT. Let me give you a special case. By any chance, if I will become IC, or by any chance the refractive index, sorry, if I becomes IC, what will be the refracted angle? Can anyone tell me? What will be the refracted angle for I equal to IC? 90 degrees. Exactly. So R will become 90 degrees. So can I say that sin I, right? I'm writing it as sin IC divided by sin 90 degrees will be equal to, if eta 1 is 1 for air, for air I'm taking, as well as eta 2 I'm taking it as some eta. Then can I write it as 1 by eta? And you guys clearly know that sin 90 degrees is nothing but 1. So from here I can write sin IC as 1 by eta. If you want eta, you can write it as 1 by sin IC. So this formula is also most famous. Whenever a light ray is traveling from denser medium to air, you can directly use this formula. Denser to air only, you must use this formula. Other than that, you can never use this. Please make sure. This is our general formula. The most accurate formula I can say. Okay. Ray travels from denser medium to air. And at critical angle only I have taken my. At critical angle. Please don't get confused. Okay. Hope that is clear. Shall we proceed further? So sin I by sin R equal to constant, you guys are saying, right? That constant is nothing but ratio of refractive indexes. Or I can write this one as eta 1, 2. Okay. Eta 1 by eta 2, I can make it as eta 1, 2, right? That's what we are taking there. Okay. Let me switch this. Okay. Now let us go for applications of total internal reflection. Applications of total internal reflection. So now you guys learned that what do you mean by total internal reflection? What do you mean by total internal reflection? So you guys always knows that by any chance if incident angle is greater than critical angle, then we can see that the ray is reflected instead of refraction. Reflection phenomena will take place instead of refraction. So we can clearly say that it is total internal reflection. Okay, at an incident angle greater than the critical angle only it will happen. Okay, fine. This we have taken earlier. So what are the applications of it? So where we are using, in what situations and what scenarios we are using this? Let me say that assume you are having a summer day. So on a summer day, so I'm just taking the road like this. This is a road. And on the road, I can say the road is here exactly. So the remaining are the layers. Layers of air. Okay. Fine. Layers of air is taken like this. Assume that I have taken a tree in this fashion. Yeah, I should run now. Okay, I have taken a tree in this fashion. Now what will happen? So, once from the sun, light will fall on it. Assume that the light is getting reflected in all the 360 degrees. I have taken one of the rays. Okay, one of the ray is coming and hitting. These layers I have taken. No, these layers are layers of hot air. Layers of hot air. Whenever the air is in contact with the surface, will get hot. Okay, so only we are getting as hot air, and hot air is always a bit rarer. Okay, so you can see that from upper layer is more denser than the lower layer. I can say that the density, I can say denser property of the medium will decrease whenever you are going to the lowermost layers. Okay, clear? Fine. Okay, these upper layers are more denser and lower layers are way rarer. Why the upper layers are more denser? These are a bit cold, right? Oh. These are a bit cold air when you compare to the layers in contact with the surface. Even this may be a bit misleading. Yeah, here I'll make it more clear. Here it will be hot air. So hot air will be more rarer. So the cold air will be more denser. Light is traveling from denser medium to the rarer medium. What will happen when a light ray is traveling from denser medium to rarer medium? It will try to take bend away from the normal, right? So we can clearly see that it will try to take a bend like this. Okay, here also we can draw. So again, it will try to take a bend like this. Here also we can draw. Again, it will take a bend like this. At one point of time, instead of taking a bend, it will be reflected back into the same medium. So if you guys are here while watching this phenomena, you will feel that, okay, when we retrace the path of the ray, your mind will say that, okay, these light rays are coming from somewhere from a tree, which is here, like this. Okay. You will see the top portion like this. Okay, like an image, like a mirage, we'll say, mirage formation. Like a mirror image kind of thing, you'll see. So you'll feel that, okay, there is some water. Okay, not only that, in deserts or in summer seasons on the roads, we'll see this phenomenon. Why this phenomenon is happening? The light ray is traveling from denser layers to the rarer layers. Whenever they are traveling from denser to rarer, they're taking more and more bend. At one point of time, you can clearly see that the incident angle, if it is greater than the critical angle, the ray will be reflected back into the same medium. Due to that, you are seeing that, okay, there is some water. So from water only, we are getting this mirror reflection like that. In deserts as well as on roads, you can see this phenomenon clearly. Fine. Shall we switch further? Even they'll say that brilliance of diamond. One of the applications of TAR is nothing but mirage formation. You can write it here. Next one, you can go with brilliance of diamonds. Brilliance of diamond. They'll say that how the diamond makers will make a diamond, in what fashion. But the diamond makers will always make a diamond in such a way that whenever the light enters into the diamond, it should suffer total internal reflection. Okay, they'll cut the edges in such a way that they'll cut the edges more suitably, in such a way that the light ray, whenever it is entering into the diamond, so it will always suffer total internal reflection. Okay, even you can get the critical angle for air and diamond interface. For air and diamond interface, IC value will be 24.4 degrees nearly. Okay, so whenever what is the brilliance of diamond makers, they'll say. So you can say that diamond makers will cut the edges. Like a 2 more question or 1 more question, there is a probability. Diamond makers will cut the edges of a diamond in such a way that the light which enters in the diamond will always suffers total internal reflection. Okay, is that clear? Not only that, even you can say that prisms are designed in such a way that whenever a ray of light is entering, so it will also try to get reflected back like that. Okay, by any chance anyone knows what is a critical angle for a prism? So we have more and more prisms, which are right angle prism I can have, an inverted prism I can have, different prisms I can have. Okay, so we'll try to solve some sums based on that one too. Okay. So now than prisms, I can say that optical fibers are main. What are optical fibers? Usually what are optical fibers? So you can see that, okay, if I make a rough diagram like that, yeah, we'll use those optical fibers in data transfer. Good. So within this, I can make one more shape. And within this, I can make one more. Core cladding and all those things I can mention. Okay. Okay. This edge part is known as core, from where the light is entering into the optical fiber, we can say. Okay. So light will enter into the core with some speed. Okay. And one more thing, this will have a refractive index as, let me call it as some mu1. Right. Now, this will have a refractive index of some mu2. Okay. Not only that, usually what will happen, mu2 will always be greater than mu1. It means that what, by any chance, if mu2 is greater than mu1, what will happen? Oh, not mu2 is greater than mu1. I can say mu1 must be greater than mu2. I just change this expression. Mu1, it must be denser. Mu2 must be rarer medium. Sorry. Okay. Mu1 must be greater. So if light enters within this, assume that light is trying to enter in this. So the moment it enters, right after that, what will happen? Light is entering from, this is a denser medium. I can say this is denser, as well as this is rarer. We will design the optical fiber in such a way that light will always enter through an angle which is greater than the critical angle. When light enters into the optical fiber which is greater than critical angle, what will happen? There will be total internal reflection, right? So when light enters into it, it will always try to suffer this total internal reflection like this. So it wants to go here. So again, if I construct a normal, this is a rarer medium completely. Oh, sorry, it must be smaller, much smaller. It must be a rarer medium, denser to rarer it is entering. So I can say that it is going like this. Total internal reflection happening each and every time. I can say that there will be 100% data transfer. And they are more reliable too. What we are using the fact, we are saying that the core is of higher denser, as well as this one is known as cladding. Okay. Core and cladding will say. Cladding is made of a bit lower refractive index. Core is made of a bit higher refractive index. That's it. So core is made of denser medium a bit, and cladding, I can say that a bit rarer part. Clear, ma? Light is entering from core. So light, this is purely optical medium, like a transparent glass kind of thing, core as well as cladding. So when light is entering through this core, Okay. Here light is entering from denser medium to the rarer medium. As this is rarer medium, if the incident angle is greater than the critical angle, we'll see that the ray will be reflected internally. It is reflecting, it is suffering total internal reflection each and every time. It is not entering into the other medium. There is no loss of light energy. We'll use a device in such a way that whatever the electric signals you are sending will be converted into light signals. Okay, we will use a device known as transducer. Transducer is a device which changes one form of energy into other form of energy. Usually current pulses you will send. That current pulses will be transferred into light energy. So the light energy will be traveling in through these optical fibers. Right after that, the transducer will be connected. It will be taken into electrical signals. Whenever this phenomenon is happening, even though through longer distances, as you are using optical fibers, there is no loss of data. Okay. How we are doing that? We are sending the light from denser medium to rarer medium. Core is denser medium and cladding is the rarer medium. As denser medium to rarer medium, as it is greater than the critical angle, so I can clearly say that the light ray is suffering total internal reflection and passing through the other end. Is that clear? Fine.